during the talk. So it's a great pleasure that we have Jonathan Oppenheim with us today. Jonathan has been a university research fellow at Cambridge University until recently, but has now, as I understand, moved to a university college in London. And he's going to talk today about fundamental limitations for quantum and nanothermodynamics, which sounds very exciting to me. He's also an expert in quantum information theory, and he has done work on quantum gravity. And we're very happy to have such a big audience here today. So at the end of the talk, there will be a chance for questions, and Jonathan has asked that if you have questions during the talk, you can also ask them in the chat, and he will have a look at that. And we will also be monitoring the audio stream, the Q+ stream for people who are watching the streaming and who are not in the hangout, and we'll try to bring those questions into the talk. So I think that's all I wanted to say. Thank you very much, Jonathan. Please start.
Okay, well, thanks. Can people hear me all right? No? Oh, really? Yes, okay. I'm getting a yes. All right, good. Well, thanks a lot for inviting me to give this talk, and thanks a lot to those who've set up Q+, because I think it's really, really great. I can do a talk wearing a bear costume beneath my waist. So I'm going to be talking about fundamental limitations for quantum thermodynamics. And let me just, I'll disappear now and just show you the screen. So I'll be able to see you, and if you want to ask a question, you can just pop something in the chat, and I'll take a look at that. Good. So I'm going to be talking about some joint work with Michał Horodecki, and it's also, I'm going to include some work with Fernando Brandão and Michał Horodecki again, and Joe Rennes and Rob Speckens. And both papers are available in the archive, and there's also been some related and independent work from Johan Alberg as well, which I'll highlight at some point. So what we're, I guess, interested here is thermodynamics in the quantum regime, and it could also be thermodynamics in the microscopic regime, or nano regime. So what I'm going to talk about is applicable in the quantum case, but also is relevant even when the systems aren't quantum, but just small or single systems, or actually even highly correlated systems. And I think thermodynamics, there's been, I would say, you can, I think, roughly divide up into three rough eras. So I think the first way, when thermodynamics was originally started, in kind of the 1800s, early 1800s, people were just getting a very phenomenological description of thermodynamic behavior. So people were, doing experiments where they were, for example, converting heat into work, or converting work into heat, and it was a very kind of, I guess, experimental and very phenomenological era of discovering the laws of thermodynamics, due to people like Carnot and Joule and Kelvin. And then I guess Maxwell started calling something statistical, I think he called it statistical statistical or thermomechanics. And it was kind of a second wave of thermodynamics, where people were essentially finding out that there was that you could explain thermodynamics through statistical mechanics. So you, through probability theory and through just the laws of large numbers, or just the fact that you had many particles, you could explain the laws of thermodynamics. So that's due to people like Maxwell and Boltzmann and Gibbs, this kind of second wave. And I think what we're seeing now, and this I think started quite a while ago with people like Landauer and Bennett, is a third wave of thermodynamics, a third era of thermodynamics, where we're starting to see that behind this statistical process, behind thermodynamics, there's information theory lurking there. And we can explain a lot of what is going on through information theory. And I think kind of one of the highlights of this approach is when Charlie Bennett excised Maxwell's demons by looking at the cost of erasing memory and Landauer's erasure, that's principle, which allowed him to excise Maxwell's demons. So I think this was probably one of the first triumphs of information theory, applying it to thermodynamics. And I think we're starting to see now, in the last couple of years, we're starting to see, I think, a whole bunch, a really exciting era of this research where we're seeing some new results appearing, and I think a more kind of different phenomena appearing and exploiting what we know about information theory and about quantum information theory a lot of the time, applying this to thermodynamics and getting a lot of new results. So I've got on the slide just a few, I think, highlights. But for example, thinking of the Gibbs state, the thermal state, as not due to ignorance, but rather due to entanglement, thinking, and trying to understand what negative entropy and negative information, how that can be interpreted in a thermodynamic context. And then recently, people have been looking at small fridges and how small can you make a heat engine, how small can you make a fridge, these sorts of questions. And they're interesting theoretically, but they're also, I think, motivated by the fact that we are now able to actually build in the lab microscopic engines and very small machines. So whether it's in biological systems or in kind of nano robots and small nano machines, we're basically in the lab able to fabricate a lot of these small systems and these small heat engines. And so I think a lot of this is motivated by things which we can actually construct in the lab. Good, so at the moment I think have these phenomena, and I've highlighted a few of them in the last slide, but at the moment I think we don't really have a rigorous theory of what it would mean to have laws of quantum thermodynamics. So we just have some phenomenon, but we don't really have an overarching theory. And I guess that's in part because the laws of thermodynamics, we're always applying them when we have large systems. So we always talk about the thermodynamic limit, where we take the number of particles or the system size to infinity, and when we do that, that's when we can apply the laws of statistical mechanics. And now what we're interested in is the opposite regime. We're interested in not taking the thermodynamic limit. It's almost a contradiction in terms that we're doing thermodynamics without taking the thermodynamic limit. And so we want to do thermodynamics in this opposite extreme when we have very small systems, which could be the microscale or the nanoscale, and they may be quantum. So we're in a very different regime, and the usual laws of thermodynamics, they may or may not apply, but we need to understand better how they might apply. So this present work is an attempt at trying to develop some basic laws of thermodynamics. And so just to outline kind of the results, what we basically find, and I'll explain this in more detail, we find that there's a generic, there's a way of determining whether thermodynamic transitions are possible or not for any transitions, and that's something which we call thermomajorization, and I'll explain that. And we also find that rather than a free energy, which is what in ordinary thermodynamics determines whether state transitions are possible, we find there's at least two free energies. We're able to get these results by basically applying two areas of, I guess, techniques which have been developed in quantum information theory. And one is this whole notion of a resource theory. And in quantum information theory, we're always talking about entanglement as a resource. So we have developed a whole bunch of machinery in the field of quantum information theory to deal with what I guess we would call resource theories, where you have a certain resource and you want to understand how you could manipulate that resource. So I'm going to apply some tools that were developed in this kind of, I guess, field of what I will call resource theories, which came out of entanglement theory. And then I'll also be applying another set of tools which come from what's sometimes called single-shot information theory, where so usually we want to compress information, for example, or we're doing information theory. We have large, very large texts, for example, or which we might want to compress. So we want to compress large amounts of information. But there's also been developed in information theory the case where we might want to talk about information contained in a small amount of information, and that is sometimes called single-shot information theory. Okay. So I'll be applying these two different tools from these two areas to understand thermodynamics. Okay. I see someone's just been muted. Good. So I'll talk about. I'll apply these tools to basically try and get at a few, I guess, key ideas. One is to understand when thermodynamic transitions are possible. Another is to understand when we have reversibility and when we don't. And I'll also, if I get time, talk about when we can get look at small heat engines and the kinds of irreversibilities that happen when you have small Carnot engines. So let me I'll start by reviewing standard thermodynamics, and then I'll get into the quantum case. And feel free to ask any questions kind of after this little section or at any point. Good. So ordinary thermodynamics. So just to remind people, I'll be interested here in the case where one has, say, some system, and here we've got a box with a gas in one of the partitions. It's a box with two partitions, and it's out of equilibrium here because the gas might expand and push this wall out, and when it does, it's going to raise this weight, and we have this system which is in contact with a heat bath, and perhaps we're interested in using the system to draw work because it's raising this bucket and doing work, or we might just be interested in knowing what kinds of thermodynamic transitions are possible. Will the wall be pushed out? Where will the system end? Where will it equilibrate? Those sorts of questions. And if we're interested in those sorts of questions, then there's only actually one function of the system which tells us whether thermodynamic transitions are possible or how much work we can extract, and that's the quantity called the free energy. And in this case, it's given by just E minus Ts, where E is the energy, T is the temperature of the heat bath, and S is the entropy of the system. And the free energy basically tells us how much work we can extract. It's just given by the change in free energy. And the free energy also tells us whether we can make a transition from one state to another, and the transition is possible only if the free energy goes down. So we can draw work from the system out of equilibrium given by the free energy, and now we want to examine this in the quantum case. And in particular in the case where we have small systems. And we're actually here, so we're interested in small systems, and what we're going to do, I think one of the key things we're going to do is we're going to replace the notion of work. Instead of lifting up a weight, what we're going to do is, because we're in the micro-regime, we're going to excite an atom. So drawing work is basically, in this case, exciting an atom. So rather than lifting a weight, what we're going to do is we're going to take an atom which is in the ground state and move it to the excited state. And we can call the single unit of work, for example, we'll call it a wit for work bit, and we are going to have the work bit initially in its ground state, and we're going to excite it, and that tells us that we've done work. And here we're interested in deterministic work, so we want to make sure that we extract work, although we can easily deal with other cases where we have where we may not draw work, or we have some probability of failure. But here we're interested in, for the moment at least, the notion that we might deterministically draw work. So we want to know, can we, given some system, can we excite this work bit from the ground state to the excited state. And what we're going to find is that instead of the free energy, which is going to govern how much work we can extract, we're going to have these two free energies, one which we call F min and one which we call F max. And for those of you that are from quantum information theory, they're very closely related to the distillable entanglement and the entanglement formation. Just to kind of preview that. Okay. Are there any questions so far at all? Okay. Good. So, as I mentioned, we're going to combine a number of elements which come from quantum information theory. The first thing is the notion of purity as a resource. You can think of it as the study of entropy. So, rather than entanglement as a resource, we're interested in purity as a resource, where if something has a lot of entropy, it's kind of useless. If something has a little bit of entropy, then it's good. And so we have this notion of purity that we're looking for. The theory of entropy, you can think of it as the theory of entropy. So we're going to use this theory of entropy. We're also, as I mentioned, going to use this notion of single-shot information theory, where if we're interested in information of a single system. And so people have been looking at combining the theory of entropy and thermodynamics with single-shot information theory, and we have some preliminary results, I guess first in 2003, and then recently with Oscar Dalston and collaborators, where they looked at extracting work from a single system in the case where you allow some probability of failure. But here it's just, there's no Hamiltonian, and one's looking at basically just the theory of entropy, the theory of information, effectively. I've got some spelling mistakes here, but the other component we're going to bring in here is energy conservation, what is sometimes called asymmetry theory, which is the study of asymmetry, or the breaking of a conservation law as a resource. So, in fact, we have two resource theories: the theory of purity, the theory of something called asymmetry, and the notion of single-shot information theory. And what we can find from this is basically we can find, using these three elements, tools from these three elements, we can basically basically find out when a transition is possible. So usually in thermodynamics we might have some large systems, and we want to know, is a transition possible from one system to another, or one state of the system to another? And here we're able to do it for any transition between a small system, so just a single molecule rather than a whole collection of molecules. And the criteria that we're going to find is called thermomajorization. And that will govern whether a transition is possible rather than the free energy. And what we're going to find is that, as well, that there's an irreversibility. So we're going to find that if we want to draw work, we have here, say, a gas in a box, and we draw work, and we find the amount of work we can draw is given by F min, so not the free energy, but something called F min. If we want to do the reverse process, we need to put in work, so we want to now go backwards. If we want to go backwards, it turns out that we must put in more work than the amount of work that we got out when we extracted work from our system. So we lose reversibility. And in ordinary thermodynamics, you have reversibility. If I draw work very slowly from a system, so if I let this piston get pushed out and extract work when this piston is being pushed out, then I can push the piston back in. If I do it very slowly, I will be able to, using the same amount of work, return to my original starting point. And there's a reversibility in thermodynamics, but what we're going to find is that there's no reversibility in the case of small systems. So let me just pause now, and what I'm going to do is try and sketch the basic ideas. And I'm going to sketch it in a very toy way, and I think a very simple way. So I think those of you that are experts might be a bit bored, but for those of you who are being introduced to this, then hopefully it'll be fairly accessible. So, starting from ground zero almost. So, what I want to show here is just discuss the notion that one can draw work, perform work, using information. So usually we have a gas, we have some molecules in the gas, and we can let the gas expand and draw work because we're pushing out a piston. But we can also extract work. We can think of this as extracting work from information. So for example, if I have a box with two partitions, a left partition and a right partition, then if I have information that there's a single molecule which is in the left-hand partition, then I can use this knowledge to extract work. So there's a connection between information and work. So what do? If the molecule is on the left-hand side, and so we know for sure that it's on the left-hand side, so with probability 1, the molecule is on the left-hand side, and with probability 0, there's no chance that it's on the right-hand side. If I know for sure that the molecule is on the left-hand side, then what do? I put a piston in the middle, but with the piston out on the right-hand side. And then I let this molecule basically push out the piston, and when it does that, it extracts work. And once I've done that, I've increased the entropy of the system because I now no longer know where the molecule is, but I've used this information, the knowledge of where the molecule was, to extract some work. So this knowledge allows me to extract work. On the other hand, if the molecule was on the right-hand side, then what I can do, I can put the piston on the left-hand side and use the knowledge that the molecule is on the right-hand side to once again extract work. So this information is power. This information allows me to extract work. And I'm using up this knowledge in some sense and extracting KT bits of work effectively. If I don't have perfect knowledge, then this is not always going to work. So for example, if I know that with some probability, say 2/3, the molecule will be on the left-hand side, but with some probability, the molecule is on the right-hand side, then what I could do is I could put again the piston so that it's pointing out to the left, and then, to the right, and then I'll be able to extract some work in the case when the molecule is on the left. But with some probability, in this case probability 1/3, I'll fail because I'll guess wrongly, and then the piston will be sucked backwards. And so with some probability, in this case, I fail. So if I have imperfect knowledge, I'm going to fail sometimes. Now, in general, this kind of holds generically. So for example, if I have a box which has a number of partitions, and there's some probability that a single molecule will be in some of these partitions, and some probability, and for some of the partitions, there's no probability, the probability is 0 that the molecule will be in those partitions, then I can use the fact that the molecule will never be in those partitions to extract work. So what do? Well, there's a bunch, in this case, the molecule is never going to be in partition 2 and partition 5, so I just rearrange where the partitions are, and then I now put a piston between box 4 and box 2 after I've rearranged where the partitions are, and I use the fact that I know for sure that the molecule will never be in partition 2 and 5. I use this knowledge to basically extract work. And so generically, the amount of work I can extract in this case is just given by, in some sense, the log of the number of different partitions minus the log of the number of partitions where I know for sure the molecule is not going to be. And that's fairly generic and tells you how much work you can extract. Now, if I'm allowed some probability of failure, then I may be happy that that maybe the molecule has some tiny probability of being in box 2 and box 5, and so in Dawson and all, they in fact looked at this case where there's some, we allow some probability of failure and extract work in this case. Now I want to look at the opposite process. So remember we had this box, this state of the system where with probability 2/3 the molecule could be on the left-hand side, and with probability 1/3, it could be on the right-hand side. Let's say that I want to now create this state. So I start with a box where I have a molecule and I have no idea where it is, and I want to go from the case where I have no idea where the molecule is to this system which has, with probably 2/3 the molecules on the left-hand side, and with probability 1/3 it's on the right-hand side. How do I do that? Well, what I could do is I could imagine that I've partitioned the box into a few more partitions, so 3 or 4 partitions, in this case 3 partitions, and now what I do is I push the molecule so that it basically, I have an imaginary line here, and I push the molecule so that there's in fact 3 imaginary partitions. If the molecule is in these 2 partitions, then it's on the left-hand side, and if it's in this imaginary partition, it's on the right-hand side. So now, once I've pushed the molecule in a bit, I don't know exactly where the molecule is, but you can see that I know that with, if I now put a barrier here, I know that with probability 2/3, just based on kind of the area the molecule was occupying, with probability 2/3, the molecule will be on the left-hand side, and with probability 1/3 will be on the right-hand side. So basically, by pushing in this molecule enough, I can basically, the more I push it in, the greater the chance that the molecule will be on the left-hand side. And so you can think of it, the higher the probability of the molecule being on the left-hand side, the more work I have to do to form this state where the molecule has probably 2/3 of being on the left-hand side. And so you can see that the amount of work I have to do to create this state is basically related to how big the single probability is. So in some sense, it's related to the largest probability. The amount of work I have to do to create the state is related to the largest probability, whereas before we saw it was just related to the number of empty boxes. Here it's related to the largest probability. So in some sense you see this irreversibility here, because the amount of work we can distill is basically for this particular box that we had, which has probably 2/3 of the molecule being on the left-hand side. For this particular box, I can distill no work because I might fail with some fairly high probability. So deterministically, I can draw no work. But the amount of work that I can, with some amount of work, I can create this state. So there's an irreversibility here. Okay. Are there any questions about that simple system? Okay. So now,
Jonathan, there's one question in Bristol.
Here.
Okay. Sandu.
Now, I know. In the previous slide, you could still use. Yeah. How do you go from the third to the fourth box?
This one to this one?
Yeah.
Oh, all I do is I put in a part. So now I basically have this area. So this area, basically, let's call it 1 unit of area. It's divided into 3 sections. These 3 sections.
Put a partition in the middle.
And now I put a partition here and remove the piston.
Now
And
move it, you can still get some work out of it.
you could still get some work, but not deterministically. So if I, because it may be that the molecule is going to be on this side of the partition. So if I care about, Lydia wants to know, so the question is basically, that Sandy just asked is, could I get some additional work after the formation process? And the answer is you can, if you don't mind some probability of failure. And the reason you might fail is because after I put this partition here, the molecule will be, with some probability, 2/3 on the left-hand side, with probability 1/3 on the right-hand side. And so with probably 1/3, I can get some work, but that's not for certain. So I'm here interested in the deterministic work of formation. Sandy, does that answer the question?
Okay.
Okay. Now, that's only half the story. As you all know, thermodynamics is not just about information. It's not just about entropy. Thermodynamics is, in fact, the interplay between information and energy. So we now want to add basically energy into the game, and when we do that, actually things become a lot more complicated. And actually initially we didn't think we would get very nice results or very simple results, because basically there's a few things you must do. Now your operations must somehow account for this energy. So I've put here that they must conserve energy. That's not necessarily the case, but there's a way of thinking about it where you can, in some sense, we have to conserve energy. So your operations are restricted in some way. And so you can't do all the operations that you could do previously. And the state of the system now, we need to account for the fact that each level, each possible partition, for example, has a different energy level associated with it. We have to account for the fact that this heat bath, which looked the same in some sense regardless of where the molecule was initially in the previous example, now the state of the system, in some sense, the state of the heat bath might depend on the energy of the system. And so in some sense, I guess a way of saying it is that the degeneracy of the heat bath is something which depends on its energy level. And so things are a lot more complicated when you add energy into the game. But we know, of course, that thermodynamics is the interplay between information and energy. Good. So now what I want to talk about is adding energy into things. And unfortunately, due to time, I'm not going to be able to get into a lot of detail, but I want to maybe just sketch where some of the ideas come from. So we're going to be using a paradigm. We're going to be, I guess, a paradigm of resource theories, which I think is part of it, partly initially due to Janzig in 2003, and it's basically, I'll explain a bit what this paradigm is, but it's a paradigm in which we could understand thermodynamics. So we're familiar with, and it's a resource theory. Thermodynamics is a resource theory, and we're used to entanglement as a resource theory. So that's the kind of the main resource theory that we're used to in information theory, in quantum information theory. But there's other resource theories. So purity, as I mentioned, is a resource. Entropy is a resource. We'll be using that, and then this notion of asymmetry as a resource. So breaking superselection rules as a resource. So we'll be talking about these different resource theories. So here's a nice little, I guess, summary of the various resource theories which we know. So we have a few different theories. So there's entanglement as a resource theory, as I mentioned. And there's a common structure to all these resource theories. And I think this is one of the great things that has come out of quantum information theory, where we have these resource theories which we can now apply to many different in many different settings. And there's different theorems that we can apply in these settings. So, for example, in entanglement theory, let's just look at the commonality amongst all these things. In entanglement theory, we have a class of operations, and the class of operations is local operations in classical communication. There's I guess the useless states, sometimes called a closed set, but maybe a better terminology is, well, so the free states or the useless states. Those are all the states that we can make under the class of operations. So under the class of operations, we can make all separable states using LOCC. Local operations in classical communication, we can make all separable states. And then what we're interested in resource theories is we're interested in understanding, how much of some resource we need to create a certain state, or how much of the resource we need to we can get out of the state. And the resource in this case is entanglement, and it's basically just defined by the fact that there are certain states which are not for free. There are certain states which are not separable, which cannot be created under the class of operations, and so we have a bunch of some resources. Thanks. So we'll have a bunch of a resource called entanglement, which is defined basically once you say what the class of operations are. Now, there's another study of entropy we call this purity theory. And in purity theory, the class of operations are just, we call them noisy operations. So we're allowed to add the maximally mixed state, and we're allowed to perform unitaries. And when we do that, what we find is that you can create basically only noisy states. Those are the only states you can create. So you can just create, so that the useless states are these states here, basically the maximally mixed state, and everything else is a resource. And so the resource is purity. So pure states become a resource because all you can do is noisy operations. And associated with this purity, there's a kind of a measure of that purity. And these are all called monotones. We have entanglement monotones, we have purity monotones, and in all these cases, in some sense, what's important here is so for example, one of the monotones is called the relative entropy distance, and in the case of entanglement theory, for example, the relative entropy distance, which was found by Vladko-Vedral et al. And Plenio, the distance to the set of separable states becomes, in some sense, a monotone, and in the case of purity, the distance to the maximally mixed state becomes a monotone, or in some sense, a measure of how much purity you have. And lastly, there's the study of asymmetry, the fact that if your operations have to commute with some group, if you have some conservation law, for example, then your class of operations is again restricted, and so the fact that your class of operations is restricted means that you have states which you can create under a class of operations, but you also have states which are somehow a resource because you could not create them under the class of operations. Okay. So Matt's asked a question which I'll maybe save for the end. Matt, is that okay? And maybe you can ask that at the end. I'm sorry, I didn't see it until now. Okay. So let me just say that by combining these resource theories, so people have combined these resource theories. For example, if we combine entanglement theory with purity, we get the study of what's sometimes called quantumness or discord. So with the Hordetskys, we show that you can, that in some sense, the study of quantumness is basically just these two resource theories combined. And what I want to talk about now is the combination of purity and asymmetry. So combining these two resource theories, and in that case, one gets thermodynamics. So it's kind of nice that you can combine these different resource theories and get things which are of interest independently. So to think of thermodynamics as a resource theory, we basically have the class of operations, which is we'll call thermal operations. So in this case, it's we're going to take that class of operations to be unitaries which conserve energy, the adding of a heat bath. So we imagine that you have a heat bath for free at some temperature, and you can use that in your processes. And now we're interested in, for example, work, and what we're going to how we're going to count work is that we have this atom, this wit, the work bit, which is initially in the ground state, and we're interested in how much energy we can add to it by putting it into an excited state. Under this class of operations, under this class of thermal operations, you find that there are some states which you just can never move out of. And that's basically just the heat bath at temperature T. So you can create, under this class of operations, this heat bath at temperature T. And in some sense, everything that is not at temperature T, is not in the Gibbs state or not at temperature T, that becomes a resource. Okay, so the class of operations called thermal operations immediately defines for us the ordinary Gibbs state and defines for us the heat bath, and defines for us the resource, which is all states which are not at temperature T. And under this class of operations, it turns out that there's a measure that you can put on states, something called a monotone, meaning it's a function which can only go down. And in the case of many systems, it's the end of this resource theory. It's the standard free energy, which is just also a relative entropy distance, but this case to the Gibbs state. And in the case of small systems, there's, it bifurcates and you get two monotones, one which is called Fmax and Fmin. Okay. So let me just say, so thermal operations, just to kind of put it in a bit more detail, we have a resource which is a system, state of a quantum system, a Hamiltonian. So here we're at, what we're doing is we recognize that physical systems, have Hamiltonians. It's not just a H equals 0, which is what's the case when you do information theory, but we have some Hamiltonian, which might be highly correlated, or local or not local, and we have some heat bath, and we have a Hamiltonian on that heat bath. So we have some thermal state, which is given here as just the Gibbs distribution over energies, and we have some Hamiltonian for the reservoir, which is given. So that's basically the kind of the initial, our initial state. We're allowed to add more Gibbs states, and we're allowed to perform energy conserving operations. And it turns out that you can think of thermodynamics in many other ways. For example, I might imagine that I have some time-dependent Hamiltonian with an internal clock or an external clock, and I apply this time-dependent Hamiltonian and manipulate my system. That's another way of thinking about thermodynamics and manipulating thermodynamical systems. I might think of all unitaries which commute with a Hamiltonian. So that's another way of thinking of energy-conserving unitaries. And I might have some interaction Hamiltonian, which I add in, so some little interaction term in my Hamiltonian, and just let the system evolve, and that's also contained in this picture. All right. Good. And are there any questions about the paradigm at all? Okay, there's a question, I think, from Ravi. What is internal clock? So I might imagine, I guess that I might imagine two pictures. One in which so usually in thermodynamics we don't really worry too much about our devices that are manipulating the working body.
John?
Yeah.
Yes, Sandy has a question, I think.
Yes. Okay. So Ravi has just asked, what is an internal clock? What do I mean by an internal clock? And there's another question from Sandy coming. Sandy, do you want to ask your question as well at the same time, and it might be related?
No, let's ask them one after the other.
Okay, good. So what do I mean by an internal clock? Well, in ordinary thermodynamics, we have some working body, and we don't worry too much about the working body. So we might, for example, have this piston. Usually in thermodynamics, you have this piston. You release the latch and let the piston be pushed out. You might kind of move things around. You might do all kinds of things. And you might turn on the magnetic field. You might turn off the magnetic field. And we don't worry too much about that. And that's because the amount of work, in some sense, the overhead, in some sense, is very small and is negligible because we're dealing with a large system. And we don't need to worry about conservation of energy or anything like that. And we might have a clock which is turning on and off these devices, and we don't worry too much about that. So we have a clock, and we look at the clock, and at some time we turn on something, and some time we turn off something. Now, in the case when you're dealing with microscopic systems and quantum systems, you need to really, because the amounts of work you're dealing with are so tiny, you have to really be careful about how you account for all forms of energy. So that's why we kind of have to be so rigorous about kind of looking at, say, only energy-conserving operations, or if we add in a Hamiltonian with some interaction we want to be careful how we how we turn on that Hamiltonian with the, sorry, I should say what the initial state of the system is, whether that initial Hamiltonian is adding to the energy or not. And so we need to be a bit careful how we deal with this. So I guess that's why we look at energy conserving unitaries. And when I say internal clock, what I mean is that we now, because we have all these other devices, then what I mean is that we need to include the energy of the clock into our calculations in some sense. So that's why what I mean by we need to make all the devices in some sense internal. We need to account for their energy. We need to account for everything essentially because we're dealing with such minute amounts of work. Sorry, that was a bit of a long-winded answer, but Sandy, so Ravi, let me know if that doesn't answer your question, and maybe I'll take Sandy's question at this point.
Well, you know my questions, don't you?
I do know all your questions, and I'm happy to answer them now or towards the end of the talk.
And you just avoid giving an answer to the question of the clock. First of all, if your Hamiltonian commutes with the unitary, then it means the clock never exchanges energy with your system.
Oh no, so sorry, these are three different paradigms. So I can imagine that in the kind of in a standard approach to thermodynamics, we might have we might just have a time-dependent Hamiltonian, and now what we need to do is we need to that's with an external clock, and so what we need to do is we need to make the clock internal, and when we do that, when we make this clock internal, then we get back our picture of energy-conserving unitaries. Likewise, you might imagine a paradigm where I'm only allowed to do unitaries which commute with a total Hamiltonian, and again, that's equivalent to energy-conserving unitaries. So these three paradigms are all equivalent to just considering energy.
So do you consider the clock getting internalized?
Sorry?
You consider the possibility of the clock getting internalized?
Indeed, yes. And I think this is where we'll disagree, but one can take the case where your clock is exchanging energy and getting, and in fact, when I say internal clock, that's exactly what I mean, where basically one includes the clock in the system and allows it to exchange some energy and be brought back in a state which is slightly different from its original state.
And in that case, how do you guarantee that the given unitary is obtained?
So, in some sense, you sorry? Well, so this unitary might not be implemented exactly at that case, and so you will be implementing the unitary approximately. So then you need to look at that case where and that's in some sense built into the paradigm because when we go to the approximate case, you might not want to form the state exactly. You might be happy with just some state which is close to your original state. Okay. Good. So, okay, we're actually very close to. I guess I have 10 minutes left. So let me just say that you basically get these. These are your. So the generic. So you can basically crank, in some sense, through this machinery of. Once you have this resource theory, you can now look at the look at when transitions are possible or not, and basically what you find is an if and only if in terms of how much work you can extract from a system and how much work is required to create a system, and it's given by these two quantities which we call f min and f max, and we allow some probability of failure here, and the quantity f min is also been independently introduced by Johann Alberg in a related context, and you basically it's a bit of a complicated expression, and the way you allow for some probability of failure, it turns out that there's a very efficient algorithm for computing this function in terms of computing what this F-min is, what this free energy is in the case of a probability of failure. You can very easily compute this quantity efficiently, basically it's related to when the Hamiltonian is zero, it's related to the rank of the system, of the density matrix of the system, but it basically is some more complicated expression with Boltzmann weights here. And likewise, the amount of work required to create a state is related to the largest eigenvalue, but it's kind of relative to some Gibbs state. So what these are, in fact, is they're basically information distances, and they were introduced previously by Nalangela Datta and by Wang and Renner, and they're basically information distances between any two states. So you have usually the relative entropy distance, which is a distance between two states, rho and sigma. Well, you can also have these other single shot, in some sense, information distances called d min and d max, which were introduced previously. And what we find is that they are the quantities which determine the rate at which you can draw work or which work is needed to create a state. And it's the distance to the thermal state. So you have the Gibbs state here in red, this thermal state, and then the distance between rho and sigma to that state is what's important for determining thermodynamic transitions. And that's very similar to entanglement theory, where it's the distance to the maximally to the separable states, which tell you when transitions are possible. And here, it's not just the relative entropy distance, but it's these other single-shot information theory quantities, which tell you when transitions are possible. And so you get this bifurcation. So you get the free energy, which was a relative entropy distance to the Gibbs state. There was a single quantity which determined when transitions are possible in ordinary thermodynamics. In the micro-regime, there's just a single. There's, sorry, at least two quantities. Good. See what I want to. And so let me just say, if you go to zeroth order, in other words, if you ignore the Hamiltonian, you recover previous results where what's important is the rank and the largest eigenvalue. This is what I showed you with the little toy boxes earlier. When you basically ignore the Hamiltonian, you recover those kind of toy examples there. But in general, you get something rather different. However, even in zeroth order, you can kind of, zeroth order in the energy, you can see already that you get this irreversibility, as I mentioned, and the irreversibility comes from two sources. The first is basically this notion that the rank and the largest eigenvalue are just generically quite different. But the second thing is a quantum effect, and it happens because the rank of what's important, it turns out, is the rank of the state. For example, in how much work you can extract, what's important is the rank of the state in the energy eigenbasis. So that rank's important. And so your rank of the quantum state might be very small, but if I now look at the energy, if I decohere the state into the energy eigenbasis, what I find is that the rank might be very large. So due to quantum effects, you can basically get a large amount of irreversibility. Due to quantum effects, these coherences in energies, you can get a large amount of irreversibility because what's important is the rank in the energy eigenbasis rather than just the rank of the quantum state. Ravi's just asked this epsilon, whether the epsilon failure probability, whether it's related to reversibility, and not really, no. So these are two separate things. So one is that you just generically lose, even when you have some probability of failure, you still get irreversibility. So a result of this is that this, for example, this what's this state here, which is it's kind of, you can think of it as a Gibbs state with, but rather than being a mixture of energy levels, it's a superposition of energy levels. This is a pure state. You might think that I could therefore extract some energy because it's a pure state and I've got some a very low entropy state, so I might be able to extract some work from this state. Well, it turns out you can't. From a single copy, no work can be drawn from this state here. If I have two copies, I can, from a single copy, no amount of work can be extracted from this state, even though it's a pure quantum state. So here you have kind of an extreme case where you have a pure quantum state, so you should be able to extract a lot of work because it has very low entropy. And you should be able to extract a lot of work by raising its entropy. Well, it turns out you can't. And that's due to this kind of quantum irreversibility. So generically, there are cases where the amount of work you can extract is much larger than the amount of work required to create a state, this F max, is much larger than the free energy. And that is much larger than the amount of work you can extract from a state. And so you get kind of an extreme, some extreme irreversibility. Allowing this epsilon failure probability, basically what that does is it smooths everything out. So I mentioned that what's important is the rank of a system, the rank of the density matrix of the system. Well, generically you might have some, as I mentioned, you might have some small probability that say your molecule is found in some partitions, there's some tiny probability. We don't worry, we might not be too worried about that. We might allow some probability of failure. And this kind of goes back to Sandy's question. If we're not, it's slightly related. We basically allow for the fact that you might create some state or fail to still work in some cases. And compression is an example where basically, in the case when you have many copies of your system, when you go to the thermodynamic limit, you basically recover ordinary thermodynamics, you recover the free energy, and that's just because the rank of your system approaches the entropy of the system, and so or n times the entropy of the system, and so if we go to the thermodynamic limit, you recover ordinary thermodynamics. So you can view the single-shot thermodynamics as somehow being more general and what's underlying ordinary thermodynamics, and it's only when we go, so it's more fundamental, which is nice, and so it's only when you go to the thermodynamic limit that you get the ordinary free energy, but before you go to the thermodynamic limit, you have these other quantities which approach the free energy in that limit. So this is somehow a more fundamental, I think, notion of free energy. I've got 2 minutes, and maybe I'll just quickly talk about thermomajorization. So I'll just mention it without getting into the details. But we know, for example, that if you have bistochastic operations, then you can make a transition from some state rho to some state sigma if rho majorizes sigma. Well, it turns out that in the case of thermodynamic transitions, we can make a transition if and only if rho thermomajorizes sigma. And what does thermomajorize mean? Well, in majorization, we write the eigenvalues of the state in non-increasing order, and we now want to just know, so this is the majorization condition, rho majorizes sigma if the sums of eigenvalues basically are larger for any k. And in the thermomajorization case, what you basically do is you add Gibbs factors to all your eigenvalues, and that gives you now some what we call beta ordering, thermal ordering of your state, and that basically gives you a different condition, a thermomajorization condition, which basically, given any state where I plot, for example, the probabilities versus energy, I can now basically tell you, can I make a transition from one state to another? So it gives you a very easy to compute way of knowing whether I can make it, whether a transition will be possible between two states. Okay, so at the end of the time, I won't talk about heat engines, small heat engines, but let me just conclude by just summarizing the main results. So some conclusions. Well, I think in this paradigm, but in this resource theory, in some sense, the resource theory encodes the laws of thermodynamics. So the fact that you're doing unitaries is in some sense the second law of thermodynamics. If you think of the von Neumann entropy as being the entropy, you have so basically the fact that you're doing unitaries and you're conserving energy and you're doing operations which preserve the heat bath. This, in some sense, are the laws of thermodynamics in this resource theory. So you can think of it as a kind of a very basic theory of thermodynamics. We found that there's a generic this thermomajorization which tells us when we can make a transition from one state to another. And in the case of extracting work, we found that there were two free energies, and therefore there was some irreversibility. And the reason there was this irreversibility was due to finite size effects, the fact that we were just looking at single-shot systems, and the fact that our systems were quantum. Last, I'll just add in that if we have some small Carnot engines, then it turns out that in order to make them efficient, you need some probability of failure. So this is for a Carnot engine rather than for the Brownian machines that people like Sandu, Popescu, and Paul Skripczyk and Noah Linden have looked at. So for these Carnot engines, you need some probability of failure in order to get reversibility for them, and in order to approach the Carnot efficiency. So with that, I'll thank you very much for your attention. Thank you.
Okay, thank you very much, Jonathan, for this very nice talk. I think I also want to thank the audience because we're spending today from Waterloo all the way to Japan, so almost covering all time zones. I think we can maybe start by Jonathan answering the two questions we have from the live stream. And we also currently have one free space on the Hangout, so if anyone from the live stream wants to join here and ask the question from the webcam, that's also possible. And in the meantime, I would ask the other audience to announce that they have questions in the chat so we can go from one to the other. So maybe, Jonathan, you could start with the two questions from the live stream now. Thank you.
Okay. There's a question put in here by Matt Leifer, and it's on this question if between energy conserving, I think, and the notion of deterministic work. And in some sense, I guess is there a relationship between energy conservation, the fact that we required energy conservation, and the fact that we were looking at deterministic work extraction? And the answer, I guess, to that is no. These are independent concepts, or so independent notions, and I can look at energy conservation. The reason I look at energy conservation is because I want to properly account for all forms of energy, and I don't want to cheat by adding in work because my device happens to allow for that, or because I've included an interaction which somehow hides the fact that I've added energy into my system. So that's why we consider energy conserving unitaries. It's just for the paradigm. The fact that we've looked at deterministic work extraction is completely, in some sense, a separate issue. And so you could consider non-deterministic work extraction using the same paradigm. And that, I think, is probably an interesting thing to look at. Okay, there's a question from Sandu coming up as well that maybe can be asked rather than, or typed in, I guess. There's a question from Limestream Watchers. Is it fair to compare the amount of deterministically to the work of formation? Okay, so is it fair? So the question is it fair to compare the amount of work which is deterministically extractable to the amount of work, the work of formation? And I guess the answer to that is yes, as long as we are in both cases looking at deterministic work. So in the case of work extraction, we consider how much work you can deterministically extract from a quantum state. And in the case of formation, we're also interested in kind of how much work is necessary, even in the worst case, to deterministically, we want to make sure that we deterministically create a state. So in both cases, we're talking about deterministic processes. So that's a fair comparison, I guess. One could consider both cases in the non-deterministic case as well. If there's another question from the live stream, could people maybe, if there are other questions, could they maybe be restated if I haven't answered them? Because when I run through the feed, I don't always see them. Okay, so there's a question from, I mean, maybe if someone wants to ask them verbally, that's also okay. Let me know. So there's a question from Viv Kendon and Clarissa Lee from Livestream. Question about WITs. Can you elaborate how quantizing energy levels of your WIT system relates to work extraction? Can you extract only in matching size quanta? Does it relate to irreversibility? So it doesn't relate to irreversibility, and in fact we need to consider, we look at the case, for example, in our heat bath where we have very dense energy levels, and that's very important. So that's something that we don't go to the limits of the continuum limit, but we do need to take the fact that at least for the heat bath, that the energy levels are very closely spaced, because we in some sense use the heat bath to make our transitions. If we allowed a continuum, because we're looking at deterministic work extraction, we could consider a continuous system, but we're interested in the minimum amount of work we can extract. So in some sense, we'd put in a cutoff anyway, and then we may as well determine we may as well use a quantized system. So in that sense, if the WIT was continuous, it wouldn't make any difference. And in fact, the WIT is kind of, it's not just a silly name. We chose it because it doesn't matter what system you use for storing the work. And we chose a bit because we thought of it a bit like some population inversion, where you're basically where you're treating this WIT as, you can think of it as basically an excited atom, which you could later use in a laser if you wanted to, if you've got many of these work bits. Question from Tony Short at Cambridge. If you look at average work rather than deterministic, I suspect you recover reversibility and get the usual free energy. Is this plausible given your results? Yeah, I think that's certainly plausible. I mean, it's certainly the case that if you imagine running your system many times and then doing, well, they're not completely the same. So it's certainly plausible, but they're not completely the same, because when you're doing when you're looking at many copies, for example. It's the fact that you're allowed to manipulate many systems, many molecules, which is what allows you to, which is what, in some sense, you've got that advantage. If you're only going to be operating on single systems, and in the end, just average, it's a bit confusing what you're doing here, because basically what you'll do is you'll have a bunch of, you might sometimes extract work to the WIT, and you might sometimes not. And now you've got a bunch of WITs which are sometimes excited and sometimes not excited. And the question is, how do you extract work from this system? So part of the reason we went to the deterministic case is because it's much easier. There's some messy questions which you don't need to deal with, because you know exactly, you're counting for everything. You know exactly how much work you extracted. And so I could, for example, extract work sometimes into the WIT and sometimes I fail. And then at the end, I might operate collectively on this thing, or do some collective lasing process where I extract work from these many work bits. So that's a possibility. But then again, you're probably doing some collective process there of all the WITs. So in the end, it's a bit unclear what you mean by average. Not sure if that answered your question again. Question from Clarissa Lee. Is the resource theory a micro-level solution to the macro-level Gibbs state? I'm not entirely sure what the question. I'm not entirely sure what you mean by the question, but I guess the resource theory, in some sense, in the limit, we will get ordinary thermodynamics. So in that sense, yes. The resource theory, by defining the resource theory, we also naturally get the Gibbs state emerging without needing to posit the Gibbs state. So it just comes about as a state which you cannot move out of. If you have the Gibbs state, then you cannot you cannot get any other state basically with just the Gibbs state, and every other state is a resource. So in some sense, the resource theory defines the macroscopic Gibbs state. So you can think of it like that. Another way of thinking of it is that these resource theories allows us to somehow define some more fundamental laws of thermodynamics from which the ordinary laws of thermodynamics can emerge. Question from Yutaka Shikano. It's a question about irreversibility and ergodicity. So I guess in ordinary thermodynamics, for example, for the second law, you often posit certain things. You, for example, posit that ergodicity, that your evolution law is ergodic, and that there's mixing. And if you have that, then you get both reversibility and you get the second law. Here we don't. So what's remarkable in some sense is we don't need to posit either ergodicity or mixing, and we even can allow, although it's not necessary, we even allow the experimenter to arbitrarily manipulate both the system and the heat bath. So it turns out that to achieve our limitations, we don't require very precise control of the system and any control of the heat bath, but we actually allow, for the limitations, we imagine that the experimenter could control the heat bath, could control the system perfectly, could do everything, and we still get the limitations. So it's actually quite remarkable that we don't require ergodicity, we don't require mixing, we don't require crude operations. We allow the experimenters to do everything, and yet we still get these limitations. So it's basically, none of this is really necessary. And in part it's because we're looking at the von Neumann entropy rather than some coarse-grained entropy.
Okay, there's a...
So that's the end of the questions.
Time now, so there's a final question from Sandhu. Maybe you can ask that with the microphone.
Yeah, so Jonathan, there is one thing that always bothers me about the single shot, these sort of theories.
Yeah.
How do you account for the free energy that you need to build the machine that will implement the transformation? The free energy that you need to initialize the clock and so on. I understand what happens if you make it repeatedly, then it doesn't matter. But because it is single shot, you should account for them.
Yeah. So I think I totally agree with you, and it falls under I would say the category of catalytic do I want to now allow you to bring in a system and use that system as long as I return it to you in roughly the appropriate state afterwards. Yeah, and so that's a very important point, and it turns out that that the limitations hold even in that case. So if I basically allow you to use some system as a catalyst and return it to you, and now I have to return it to you, then it turns out that one still gets the limitations. The thermomajorization criteria is changed somewhat, so you get a slightly different criteria. But the actual limitations in terms of these two different free energies, those remain completely the same. So if anyone's interested, maybe just send me an email and I can send you the paper. But so that's an important question, and it turns out that these one can basically look at that case and get the same limitations.
But you have not shown that yet.
Yeah, so I'm happy to send anyone to show anyone that proof. If anyone, just send me an email and I'll send the draft. But you're right that it's not that I didn't cover that in the talk, certainly.
Okay, so I think we should wrap up. If we have other questions, we can also ask them on the Q+ stream. If you have suggestions for further speakers, you can ask them there and suggest them there. If you have technical feedback, you're welcome to hang on this hangout here and discuss them with us. But for now, let's stop the official part, and all thank Jonathan for this very nice talk, and thank you.